Okay, today I'm going to talk about the three-phase inverter, one of the subtopics of the inverter. Basically, we're going to look at a circuit. It consists of 6 switches, the controllable switches, and we have the input voltage, which is in form of the DC voltage, and then the output will be the three-phase output, which have a 120-degree phase displacement between each other. So for this circuit, we assume that we have a phase 1 here, phase 2, and phase 3. Okay, so as I mentioned in the full wave rectifier topics, the arrangement or the labeling of the controllable switches or the thyristors back in the rectifier is always in the arrangement of switch 1, switch 3, switch 5, switch 2, switch 4, and switch 6. This is very important so that you will have correct signals to the switches and you will be having a correct output at all phases there. Okay, so we're going to discuss, and for EPO510 we only focus on this type of circuit, right? Okay, so there are 3 ways, 3 techniques that we can achieve for the output voltage waveform. So it is an inverter, so the input is DC and the output is of course in the form of AC waveforms. So there are 3 types of waveform that you're going to obtain at the output. The first one, if you use a 120-degree conduction mode technique with 2 simultaneously connected devices, you will get the first type of waveforms. And then the second one will be 180-degree conduction mode, or the other name is 3 simultaneously conducted devices. And finally, if you use a sinusoidal PWM, we're going to get a pulse width modulated output voltage at the 3-phase there. Okay, so let's look at the first technique or scheme, which is known as 120-degree conduction mode. Right. Okay, so in this example, we use IGBT there, the MOSFET there, right? So this is the signals to all the switches from switches 1, 2, 3, 4, 5, and 6. So we have 6 signals, the control signals to the switches here. So for you to be able to get the 120-degree conduction mode output, what we do is you need to set or to supply the first switch with a 0 to 120-degree conduction mode, conduction point 0 degree to 120 degree, and then the following switch 2 will have a 60-degree delay from the first switch, and the following switches, switch 3, also further will have a further 60-degree phase delay from the previous switch 2 control signals, and switch 4 will have a further 60-degree delay from the switch 3, and so on until you have the final switch, which is a switch 6 control signals, which is 60-degree delay apart from that switch 5 signals. So by having that signals, and those signals are correctly fed or control the switches, the relevant or the respective switches, then you will have a correct 120-degree conduction mode. So that's why I always put emphasis on the labeling of the switches must be correct, because if your labeling of your switches is not in that arrangement, but for the control signals we have these control signals and you will be wrongly fed the switches with the wrong signals, so you will not be able to get the three-phase output with 120-degree conduction techniques. Okay, so to understand what happens to the circuit with these signals, let's look at the first point, okay, where we look at the instant of where you are at this particular point, for example, in this point, right? So if you focus on that, the only switches that on during this time will be switch 1, will be the switch 1 and switch 6, right? So which means at that instant, at this instant, we have this switch and that switch that only ons during that time. So we're going to see that your current, the flow of the current is from the supply voltage VDC through the switch 1 and then go through that path, okay, go straight to your resistor here, the first phase 1 resistor, and then come back to that second phase 2 resistors, then go through that point, go through the switch 6 and come back to the negative polarity of the VDC. So we can actually draw the equivalent circuits of these. We have positive, sorry for the drawing, it's not easy to sketch with the mouse. So we have a VDC input and it goes to that point, and then when switch 1 on, it appears as a short circuit, then it goes to that point and then come back to the phase 1 resistor, then goes to that point, back to that resistor, and then go through that point, and then go through the switch 1, it appears as a short circuit, so you simply draw a straight line and come back to that VDE, right? So for the resistor, we have a positive, negative, R value, 3 switches there, 3 resistors will have a equals value of R, so I'm going to put that as R, and then the polarity always in that direction. We have R, this is for phase 1. So this is phase 1, and that will be your phase 2. Okay, so this is a circuit, and therefore you can also simplify the circuit, and finally it will become just simply an input voltage, then goes to the first resistor, second resistor, then you come back to that negative polarity, and this will be plus minus R, and then you have negative plus R, the second one, isn't it? So this is phase 1, this is phase 2, right? So the input is always, I just put it as a V in here, this is your VE, and therefore the voltage across your both R's here will be of course equally divided, So that will be half V in and you have another plus minus half V in for the second phase. Right. Okay, so that is basically the equivalent circuit and the voltage across each phase there. So now let's look at the real waveforms, the simulated waveforms. I'm going to clear that. Okay, so therefore if you look at the output voltage waveform, so the phase 1 will be having half of the V in, so this will be half of the V in, the voltage across your phase 1 resistor, and then you have a minus V in, minus half of the V in for the phase 2, right? So let me draw again. So you have, let me draw again. So you have R1, then you have R2 there. So this is R, the same polarity, plus minus, and this is phase 1, and this is phase 2, right? So I hope you can refer to the previous slide, the previous note, whereby you have this plus half of the V in across your R, and then for phase 2 you have another negative, because the polarity is plus negative here, so you have negative V in during this time. Okay, so finally when you look at this is the phase voltage. When you look at the line to line voltage, of course is the difference between phase 1 and phase 2. So for this particular line or instance that we have just discussed, right? So we have the line to line voltage will be V phase 1 minus V in over 2, and that's why you have that 100 volt or the V in, that's equals to V in. So this come back to your V in, right, during that time. Okay, so I hope you understand that. So we have that V, how to get that V line to line. So we have to subtract V phase 1 minus V phase 2, so we have a V in over there. So I hope you can trace all of these instance for a complete 1 cycles, and we can observe that the waveform, okay, we can observe that for phase voltage it consists of 3 levels, 1, 2, 3 levels, and for line to line voltage it will consist of 4 levels of voltage, 1, 2, 3, 4. So that is what is discussed here. The output voltage waveform, phase voltage consists of 3 levels, a step voltage, whereas a line to line voltage consists of 4 levels. Okay, so since this is the AC waveforms, we also would like to look at the FFT analysis. That's what we did to quasi-square waveform. Square waveform, we always want to look at the Fourier analysis, do the Fourier analysis to get the harmonic spectrum of the output voltage. Okay, so we do that, and we're going to see that this is your the waveform, the FFT analysis of the 2 waveforms of phase 1, of the phase voltage, and the line to line voltage waveform. So if you look at the waveform, the characteristic is that it has the fundamental both has an equal harmonic contents, whereby we have the harmonics at the fundamental. There is no triplet harmonics. We have next is at 5th, 7th. There is no 9th harmonics. And then we have 11, 13, and it continues. So the characteristic will be the fundamental, all odd harmonics, but no triplet harmonics. Okay, so that is for 120 degree phase shift. And again, when you look at the signals, okay, it is also known as two simultaneously conducting devices because at any particular time, at any instant, you only have two switches are on. For example, the one that we discussed just now, we have switch 1 and switch 6, which are on, and the rest is off, and that happens. That's why it's known as the two simultaneously conducting devices technique. Okay, we're going to proceed with the second type, which is 180 degree conduction mode. And again, we have three simultaneously conducting devices, so we expect that at any particular time there are three simultaneously conducting devices operating. Okay, so let's go through the second circuit, which is 180 degree conduction mode. So we have the same, we still have the same circuit with a leveling of S1, S3, S5, S2, S4, S6, as I mentioned just now. But now we have to do some modifications to your control signals. Despite of 120 degree conduction duration of the signals as for the 120 conduction technique, okay, so this is 120 degree conduction mode. We have the switch will on from 0 to 120 degree the angle. But for the 180 degree conduction mode, we're going to let that each signals will be conducting for 180 degree angles. Okay, so we will on 0 to 180 degree, and for switch 2, again there's a 60 degree delay, but still we maintain the duration of the pulse, which is 180 degree conduction pulse. Okay, and then we have for the 120 degree for switch 3, 180 degree for switch 4, 240 degree for switch 5, and finally 300 degree for switch 6. Right, so let's look quickly. If you are at this point, let's say we are at this particular instant. Okay, so if you look at this instant, we're going to see that switch 1 on, next is switch 5, and next will be switch 6, right? So if I may sketch the equivalent circuit during that time, we're going to see that this is the input supply voltage, and again, sorry for the drawing, switch 1 appear as a short circuit, and then you will go to resistor 1, and at the same time you also have a switch 5 also on. So from that point you will go to switch 5, it goes to straight here, and this is phase 3, and now it goes to both, you go to switch R2 and connected to switch 6 here as a short circuit, and now it comes back to the negative terminal. Right, so we have now the path of the current will be through switch 1, switch 5, and switch 6, right? And therefore you have this is as a phase 1, phase 2, and we have phase 3 again, this particular resistor, okay? And it's the voltage across it will be So here you have, from there you have plus minus voltage there, and you have another phase, a plus minus voltage across second phase. We have plus minus voltage across phase 3. So if we can rearrange to get a clearer look at the circuit, we can rearrange the circuit, the equivalent circuit, so that we have the input voltage. Then you will see that the point connected to one resistor number 3, and that goes to resistor number 2. Okay, so this is R1, R3, and R2. Okay, so this is referred to that resistor. This resistor represents that one, and the third resistor will be representing that point. Okay, right. So once we have that, I think I need to clear that first. Now we're going to determine the voltage across it. So we have one, two voltage, and we have another resistor there. So this will be all resistors will be having a similar identical R value. So I'm going to get that, I put that as a R. This is R, and also this is R. So you can solve for that parallel resistor there, so that becomes plus minus, and you have only the resultant resistor there and the phase 2 resistor. So that remain as a R, but now because this is the equivalent R value, so it become half of the R across that. And the voltage is always in this polarity, plus minus. For the phase 2 become plus minus in the opposite direction, plus minus, right? So if you look at that voltage, use the voltage divider rule, use the VDR to solve for each voltage across R, a half R and R. So here you're going to get 1/3 V in, okay, and here you're going to get 2/3 V in. Okay, I'm not going to go detail on how to do that VDR, so I hope you do yourself. Try to get the voltage across. It will be 1/3 of V in, and that will be 2/3 of the V in. So now let's focus on the. So remember, you have half 1/3 V in across phase 1 and phase 5. Phase 1 and phase 3, and for phase 2 you will have 2/3 of V in, but of course negative polarity here. Okay, so let's move on. So let's look at the voltage while we are at this particular instant. Okay, we are at this particular instant. Let's look at the voltage current. So right, so we have phase 1 and phase 2 in the waveforms. right? Just to draw it again. So this is your R1, this is R1, this will be R3, and this is R2. Okay, so that will be that phase, and this will be the phase 2 resistor. Okay, so I did mention just now, across phase 1 there is 1/3 of the input voltage. So our input voltage is 100 volt, therefore you have a value of plus 33.3 voltage during that instant. And for the phase 2, I did just show you just now that it is two-third of the V in, which is 66.6. So it's a negative polarity, so you have minus 66.66 across your phase 2. Alright, so finally we also look at the line-to-line voltage. So if you minus phase 1 minus phase 2, you will get 100 volt. Okay, and then if you trace further, for this that instant you still have 100 volt, but if we got to that point, you will see the output voltage become 0 for the line-to-line voltage. So what you can observe from these waveforms, now the phase consists of 1, 2, 3, 4 levels, okay, for phase voltage, but for line-to-line voltage it only consists of 1, 2, 3 levels. This is opposite to the 120-degree conduction mode technique that we did just now. Where for that 120-degree we have opposite waveforms. Phase will be having 4 levels, and line-to-line will be having 3 levels. Okay, so let's look at the harmonic spectrum. So again, for phase we have the same characteristic of the harmonic spectrum. Fundamental, no triplet harmonics, and we have of course all the odd harmonics but no triplet harmonics. Okay, so there's mentioned, look at the notes here, the above waveform also show that no triplet harmonics present in the output voltage. However, the magnitude, the amplitude of the fundamental component is higher than the previous conduction mode. It seems that this conduction mode is better than the 120-degree conduction mode because the magnitude of the fundamental component is higher. However, the characteristics is similar to what we have before. Okay, very simple. That's a straightforward. I hope you do okay. That is for 120-degree and 180-degree conduction mode. And finally, there is as what we did, as I was mentioned, that the pulse width modulation is really an interesting waveforms. So it is also used in the three-phase inverter. So how to produce that? The output voltage with a pulse width modulated signals. We still have the same signals circuit, sorry, S1, S2, S5, S2, S4, and S6, and then that goes to phase 1 resistor, phase 2 resistor, and phase 3 resistor. So to produce the correct PWM waveform, again, the pulse width modulations signals always the pulse width modulated signals can be achieved by comparing modulating signals, sinusoidal modulating signals, in this case sinusoidal modulating signals, with a triangular carrier signals with a high switching frequency. Okay, so what that's what we have to do. So let's look at carefully how to produce that. So you need to have 3 comparator, and you're going to compare the 3-phase supply voltage V red, V yellow, and V blue with a triangular carrier signals. Okay, so you compare with the same carrier signals, and the output of that whenever modulating signals is greater than the carrier signals, you will create logic 1, the output will be 1. When V modulating signals lower than the carrier signals, produce 0 out of the comparator. So let's focus on the first S1 and S4 signals. So the output of that comparator will be connected to S1, and the inverting version of that signals will be fed through the S4. The same leg, this is first leg, second leg, and third leg of the device. So they work anti-phase. Whenever S1 on, S4 will be definitely off. S3 on, S6 will be off. S5 on, S2 on. Okay, so that is the circuits and also the comparator circuits. Whenever you are asked to sketch the wave, to draw, to explain, always draw this circuit, and then you describe how to generate the PWM signals. So as for the PWM signals to the switches, this is the blue. The blue waveforms is the triangular carrier signals. Of course, high switching frequency, and then you compare with we have a three-phase modulating signals, red, yellow, and blue modulating signals. You compare with the triangular carrier signals. So this is a bipolar technique. We have both positive and negative triangular carrier signals. So you compare that and then fit through the respective switches, and this is what you observe in the output waveforms. For phase voltage, it will consist of basically 1, 2, 3, 4, 5 levels of phase voltage, and the line voltage only consists of 1, 2, 3 levels of the output voltage waveforms. But of course, the beauty of the pulse width modulation signals, modulated signals, lies when we look at the harmonic spectrum of each of the voltage, output voltage. So if you look at the waveform again, now you see that it consists of fundamental, and I believe this is switch. The carrier signals is at 1.5 kilohertz. Okay, it's switched at 1.5 kilohertz. If you look further, there is no harmonic at the switching frequency. Okay, there are no harmonics signals, harmonic contents at the switching frequency, even odd multiple or even multiple, there is no switching. So it has a fundamental. There are no no low order harmonics, but the next harmonic is around the switching frequency and its multiple. Right? So that is the beauty of the PWM technique waveforms. So in order to remove this, I think I've shown you before, you can easily remove the higher order harmonics by using a low pass filter, and you can simply get rid of the harmonics, and what left is only the fundamental sinusoidal signals at the output, a very fine quality of output signals. So that's it. That's basically what is a three-phase inverter. You can try to simulate to get all these waveforms and try to explore all the waveform, looking at the harmonics, contents, and the circuit operations. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.